So today I'm going to talk about quantum computing. I will start with basics and then talk about some algorithm and hardware. So this is pretty superficial. We cannot go deep. We have about 4 hours in the coming 2 weeks, and it's impossible to understand everything. And the assumption that is that you don't know much about quantum computing. But through these 4 hours of interaction, I hope that you can get a basic understanding of what quantum computing is about, how the algorithms work, but more importantly, their limitation. Right? Quantum computer is not everything. It's not going to replace our classical computer. Right? So that's why we need to learn what it is. And as an engineering student, if you don't do quantum physics, you will find that you play a very important role in quantum computing, from programming to electronic controls, right, and algorithm development. So this will be my outline. First, I will talk about myself, give you an introduction. So in these 2 classes, first I will give an overview of quantum computing, in which we will introduce some important concepts. Then I will have a more technical part to talk about quantum gates, how each quantum gates work, and actually they are very simple. They are as simple as a simple matrix multiplication. I will use Deutsch algorithm as an example so you can appreciate the power of quantum computing, how quantum parallelism is achieved. Although this might not be practical, however, it illustrates some of the very important concepts. I hope I can cover part 1 to part 3 today. And then next week, I will talk about quantum computing hardware. I will use superconducting qubit and silicon spin qubit as examples, so you can understand what are the criteria to implement quantum computer and what are the challenges that we have now. If we have enough time, I will talk about other qubits also, including the photonic qubits and trapped ion qubits. Okay. So first, about myself, I'm from San Jose State University. I will talk about my book and also the quantum technology education here. So as Professor Chang just mentioned, a huge chunk of my research related to semiconductor device and physics. We do a lot of simulation, from atomistic simulation to nanowire to power electronics such as wide bandgap device and system and multi-physics simulations. We also tape out chips. We think that these chips are important because they will be measured at 4 Kelvin. 4 Kelvin is the boiling temperature of liquid helium. This is a very low temperature, but it is not low enough for quantum computing. However, later you will see that we need low temperature electronics as low as 4 Kelvin, right, to control quantum computers. Nowadays, we still use room temperature electronics to control quantum computers, but that is not scalable, right? And that's why we study the integration chips, integrated circuits at low temperatures. At San Jose State U, we are at the heart of Silicon Valley. If you have been to here, near San Francisco, and we have a lot of students, 36,000, and this year actually 40,000 students. But we don't have PhD degrees in general. In electrical engineering, we have about 200 master students and 500 undergraduate students. We have quite many students come from Taiwan actually. And many of the students work in the technology company here in Silicon Valley. And actually, like Cisco, Apple, they have their most employee coming from San Jose State University. In the Master of Engineering, we also have a specialization on quantum computing, right? Because we believe that electrical engineers play a very important role in quantum computing, right? So we have quantum algorithm, we have quantum computing architecture, and more importantly, we have low temperature electronics, cryogenic nanoelectronics. At the same time, we also have a Master of Science in Quantum Technology. This is a joint program between electrical engineering and physics. It's an interdisciplinary program, which is pretty interesting. So my final advertisement, like what Professor Chung just mentioned, I have 2 books. One is Introduction to Quantum Computing, from a lay person to a programmer in 30 steps. Because I'm an electrical engineer, I study quantum computing myself, so I think I understand the problem for a typical engineer when they study quantum computing. So I try to go from very basics. I don't assume much linear algebra knowledge, step by step, until they can understand some of the common quantum computing algorithm, such as Shor's algorithm. Another book is Quantum Computing Architecture and Hardware for Engineer. Again, it's step by step. In this book, I cover superconducting qubit and also silicon spin qubit. At the same time, I also writing a book on trap ion, photonic, and neutral ion qubit, and they can be found on arXiv. And as Professor Chung said, I have a YouTube channel. I record my class on quantum computing algorithm here and quantum computing architecture here, right? You feel free to email me if you have questions. I can send you the links. Okay, so these are all my advertisements. So now we will go to the meat of quantum computing. Again, I will start with something very basic. Bear with me. If you have questions, you actually can ask now. You don't need to wait until the end. I plan to conduct this lecture slow enough. I hope that every one of you can learn something in this lecture. I don't want that you need to go back to study again. Okay? So the first part, I would like you to understand some important fundamental concepts. You can appreciate what is quantum parallelism and why it is important to have superposition, entanglement, and the role of measurement and error correction in quantum computing. Okay, but more importantly, while you can see the power of quantum computer, I hope you understand that quantum computer cannot replace classical computer, but it is a great accelerator. So what is the application of quantum computer? Right. First of all, quantum computing uses 2 quantum phenomena called superposition and entanglement. Now, we have been using quantum mechanics in our daily lives for many decades. Your computer has transistors, right? The projector has LCD. Even your laptop has display. They all use some sort of quantum theory, quantum mechanics theory, to make it work. But nowadays, what we're talking about is to use superposition and entanglement directly to do computation. In my opinion, interference is also very important in order to make a useful quantum computer. There are 2 types of quantum computer. One is gate-based, just like a classical logic. You have different gates. In classical logic, you apply a NAND gate, NOT gate, or a gate to do computation. In quantum computer, you also apply some quantum gate to do computation. But they are different, which we will discuss later. Another type is quantum annealing. Quantum annealing is like using quantum physics to find the minimum energy of a system. This is particularly useful for some optimization purpose. And because it's quantum annealing, we expect it basically is like you start with a certain configuration, right? This is not in real space, just some configuration space. And you try different annealing method. You hope that you will go through the barrier and then find the minimum energy, which is the solution of a problem. Now with quantum annealing, you might have quantum tunneling, just like you tunneling through the barrier. That is a possibility to help you find a solution much faster than classical annealing. But again, today we will talk about gate-based model like this. And probably you know already, and Professor Chang is an expert in quantum finance, right? I am actually learning from him. He also helped us supervise a master student on quantum finance. And that is because if you can use quantum computer, there's a possibility you can find out the best solution, best portfolio, a little bit faster than your competitor, and then you will earn a lot of much more money. Earlier this month, I believe IBM and Hong Kong and Shanghai Bank, HSBC, right? They announced a breakthrough in their quantum finance algorithm, right? Whether it's useful, no one knows, right? And if it is really useful, I don't think they will disclose, but probably that's a technical breakthrough. It can also be used for quantum machine learning, secure communication. More importantly, it can speed up some of the very difficult computation. And that can help us to design better battery, better drugs for health, for human health, and design more sophisticated engineering object, right? That is very important. So quantum computing are important, but their basics are not that difficult. Let's first talk about states and superposition. So in classical computer, you probably know already, we represent information in 0 and 1, right? For example, you can say head is 0, tail is 1. Use the coin. You can represent information faithfully just using this classical object. Even I can use happy and sad, but of course what we are doing now is use transistor. When transistor is on or off, they are 0 or 1 respectively, right? So information are represented by state of a physical object. In quantum computer, we also have something called basis state. What is basis state? They are just like classical state. So they still also have 0 and 1. In this particular case, we put it in something called cat notation. We will just take it as it is. Okay? So that is a way in quantum mechanics we write down the state of a system. So if we only talk about the basis state, it's no difference between quantum computer and classical computer. Again, I can have head and tail, happy and sad, and open and short switch. They're exactly the same as a classical computer. And that's why when you learn quantum computing, it is okay to link it to a classical computer at the beginning. What is really different is that quantum computing allows the so-called superposition. Instead of just 0 and 1, I can have a state which is a linear combination of 0 and 1. For example, I have alpha 0 plus beta 1, where alpha and beta are complex numbers. For example, 0.5 I plus 5 plus 0.1, for example, right? So this is a complex number. So you can see that it's a linear combination. To understand this, it is not very difficult. You can think of our coordinate system. For example, if I have a two-dimensional system, this is in our real space. We have x hat, we have y hat, and any vector, right, v, may be equals to alpha x hat plus beta y hat. And this is just like what we have in classically in our two-dimensional space. But here is something we call Hilbert space. It can have a 0 and 1 state as the basis state. And then any state can be represented as a superposition. As an analogy, this is just like a coin spinning on the table. Is it head or tail? We don't know. But it's a superposition of head and tail. And this is what makes quantum computing powerful, because it allows superposition. So now here we say that this is a 1 qubit system. It's not difficult to understand, because to store 0 and 1, I need 1 classical bit. So similarly, this is 1 qubit, 1 quantum qubit. A 1 quantum qubit has 2 basis states, and it can represent any state as a linear combination of the basis state. Nothing special, right? But what if we have more registers? In a classical register, we have 4 bits. It can go from 0, 0, 0, 0 all the way to 1, 1, 1, 1. So you have 16 possible values. 1, 2, 1, 2, 0, 1, 2, all the way to 15. Now, we can also have a 4 qubit quantum register, right? This is a 4 qubit quantum register. So because it has 4 qubits, so it has 16 basis states. Again, these are basis states. They are the same as their classical counterpart. However, you can form a superposition of these 16 basis states. For example, a general state can be equal to A0 times 0 plus A1 times 1 all the way to A15 times the last basis state. Of course, when I say 15, because this is 1, 1, 1, 1, I just write it in a decimal number. So describe 4 qubit, you need 16 complex number. So in general, if I have n qubit, then I need 2 to the power n complex number in order to describe the system. So what's so special? Let's think about what if I have 300 qubits. For example, I have 300 electrons. I use the spin to represent the quantum state. Then I will need 2 to the power 300 complex number to describe the state of 300 electrons. This grow up exponentially. 300 electrons are countable, right? Not a lot, you just count them. Your college might have more than 300 students. But in order to describe 300 electron spin state, I will need 2 to the power 300, which is 10 to the power 90 complex numbers. So there is a lot of information in a quantum state. For example, there are less than 10 to the power 82 atoms in the universe. There are less than 10 to the power 21 bytes of storage in our world, including your computer, including my computer. So we almost cannot describe the complex number by just use the storage that is available in the world. So this is a very powerful quantum memory in some sense. Yes, it is very powerful, but remember, how do we write the information? How do we read the information? It's not easy or almost impossible, right? So it doesn't mean that we find a good thing already. But the most important thing, I just want to let you know that there's lots of power in superposition because we cannot even store the complex numbers. That is the first thing. Secondly, because quantum mechanics is linear, so if I have a state, you see this state is a superposition of 0, 1, 2, 3, because this is a 2-qubit state. Basically, if you forgot, this one means 0, 0, this one means 0, 1, this one means 1, 0, this one means 1, 1. I have 2 qubits because I have 4 basis states. If I apply a function, an operation to this superposition state, it is equivalent to applying the function to all the basis states at the same time. And that is called quantum parallelism. I can compute many things at the same time. And this is true. The only difficulty is how do we get the information, or how do we do some meaningful computation? We really do everything everywhere at one time. It's just like a parallel universe. So superposition is the key to allow quantum parallelism. Using one hardware, we can compute one copy of hardware. We can do a parallel computation very fast. Okay? So quantum computers are important because it allows superposition and quantum parallelism. Let's talk about is another special property, measurement. What is measurement? Just like the spinning coin, you say that it is a superposition between head and tail. Okay, then whether is it head or tail? If I don't measure it, I don't know. I really don't know. What would I do? I need to stop it through measurement. Then it will collapse to either head or it will collapse to either tail. That is the same in a general quantum state. This is a 1 qubit quantum state, as you can see. It has two basis states, 0 and 1. When I do a measurement, it will collapse to 0 or collapse to 1. Completely random. And that's why Albert Einstein said, the God doesn't play dice, because he doesn't believe in quantum mechanics, or he didn't believe that quantum mechanics is complete, because he didn't like the randomness in quantum computing. But anyway, this is true. Your measurement will collapse the states randomly to either 0 or 1, except that the probability that it will collapse to 0 or 1 is proportional to the magnitude square of the coefficient of 0 and 1. Okay, so this is 1 qubit. If you have 2 qubit, then, for example, this one, if I have 2 qubit, then it will randomly collapse to 0, 1, 2, or 3. Okay? Fine. So we're done. Measurement is special. That limits a lot of application in quantum computing. Now, there is another property called entanglement in quantum computing. Now, you ask yourself, how many qubits do we have here? As you can see, this is a general state. It is a superposition of 0, 0, 0, 1, 1, 0, and 1, 1, which is 0, 1, 2, 3. So it is a 2 qubit state, right? Because I have 4 basis states. It's a superposition, so its coefficient is 1/2, -1/2, 1/2, and -1/2 for this one. Now, this state can be factorized into 2 product states, what we call the tensor product. Tensor product is something more advanced in linear algebra, but it is nothing difficult. It just tells us how to combine 2 smaller systems into a larger system. I have 2 electrons. Each of them has its basis state of 0 and 1. So how do I describe these 2 electrons together as a system? Right? Just like myself and my wife. Myself, you can describe me with some characteristic. You can describe my wife as some characteristic. And we together form a family. You can also describe us with some characteristic. Now, for an entangled state, you can always factorize them into 2 subsystems through tensor product, which means you can describe the first electron by this state and describe the second electron by this state. So you don't have extra information when you describe them as a whole system. Electron 1 now is a superposition of 0 and 1 and it is 0 plus 1. Electron 2 is at 0 minus 1 superposition. And then the whole state is this. This is not interesting. Any unentangled state can be simulated efficiently using a classical computer. So if they can simulate by classical computer, there's no point to do quantum computing. But there are some states called entangled state. For example, this entangled state is a superposition of 0, 0 plus 1, 1. It doesn't have 0, 1. It doesn't have 1, 0. Because their coefficient are 0. Basically, this is 1 over square root 0, 0 plus, basically, I can also write this as the whole thing plus 0 times 0, 1 plus 0 times 1, 0. These states cannot be factorized by two subsystems. You cannot do that mathematically. So it contains more information than electron 1 and electron 2 themselves. Okay? And this is the important things that allow quantum computer to speed up a lot of computation, because it gives some extra states that classical computer cannot access. It's also instructive to just feel what quantum entanglement can do. But here we're trying to show you something called spooky action. It is not really spooky, but it is something that confuses us. Something makes us feel very strange. Something makes Albert Einstein feel that quantum mechanics is not complete. For example, we have two electrons. We make them in an entangled state. Remember, the entangled state I give you is 0, 0 plus 1, 1. But for electron with a spin, 0, 0, 1, 1, adjust the name. 0 may be represented by spin up. 1 may be represented by spin down. So do not worry. We are talking about the same thing. This is just equal to 0, 0 plus 1, 1. So they are in entangled state. Now, I then move one of the electrons to really, really far away. Let's assume that they are still entangled. Then the state is given by this. Still given by this state, right? Because they're still entangled. Now, what if I do a measurement on the electron next to me? What happens when we do measurement? The wave function will collapse, right? It will collapse to one of the basis state, right? And the probability you will collapse to one of the basis state is proportional to the coefficient in front of it, right? We just talked about that. So I have 50% to get it spin up or 50% to get it spin down. It's completely random. I don't know. But assume that I get it spin up after measurement. What will happen to the another electron far, far away? Well, because the whole system is entangled, it will collapse to either up, up or down, down. And since the Earth electron collapsed to up, the another electron far, far away must collapse to up at the same time also. Because up, down is not an option, right? We only have up, up or down, down for this whole system, right? So that looks like I can transmit information faster than the speed of light. But no, I cannot. If we really try to do it, we find that it cannot. But still, why this electron far, far away can feel what I'm doing? So we won't go into detail. This eventually will be related to something called the Bell's inequality and lead to the violation of Bell's inequality in quantum mechanics, which has been proved correct for the violation by experiment. And the physicists, right, they got Nobel Prize because of this 2 or 3 years ago. So we don't need to argue whether there's a right or wrong. It's too much for us. A lot of philosophical question. But my goal here is to show you that quantum entanglement is something very special. And because it is so special, it is not strange that it will provide some very important operation in quantum computing. So at this stage, we have learned the basics of quantum information, right? We understand the importance of superposition. We find it is very special about measurement, and we also see the strangeness of quantum entanglement. These three things play very, very important role in all quantum algorithms. Okay, then let's talk about quantum gate. Before that, let's talk about the so-called broad sphere. Now, as we said, a general 1-qubit quantum state can be represented by alpha 0 plus beta 1, right? Now, mathematically, it happened that we can map this state to a something called broad sphere. So any state can be found on this broad sphere. For 0 state is in the north pole, and the 1 state is on the south at the south pole. Now, we need to make it very clear. This is not the space in our real 3D space. Okay, so we do not quantum qubit does not live in our 3D space. But this helps us to understand a lot of important concepts. But you need to be very careful when you use broad sphere. For now, we agree that a quantum state resides on the surface of a sphere. Then what is a quantum gate? A quantum gate is nothing but just to rotate the qubit on the broad sphere. Maybe I was here at 0 state. After applying a Hadamard gate, it becomes this plus state. Apply a NOT gate, it becomes this 1 state. And that is a quantum gate. Now, of course, you can have many qubits, then you cannot represent it on broad sphere. But every qubit still live in their hyperspace, right? A space you cannot see in a mathematical space. But whenever we apply quantum gate, we rotate the vector in their hyperspace. But what is a quantum gate after all? It's actually just a laser or microwave pulse, which we'll look at it later. It is not a transistor. It is not like PMOS and NMOS MOSFET to do a NOT operation like what we did in classical circuit. For now on, at this moment, just assume it is a laser or a microwave pulse that will rotate it on the broad sphere. Now, some quantum gates has classical counterparts. For example, NOT gate, as I just said, it will make 0 to 1, 1 to 0. Or something called exclusive OR gate. This is also the so-called control NOT gate. We will discuss more about control NOT gate. It's a 2-qubit gate, so you see that I have 2 entries in this cat state. This is the first qubit, this is the second qubit, this is the control qubit, and this is the target qubit. And this is how it works. I will talk more about this, but I want to emphasize that this is something called entanglement gate. A useful quantum computer or algorithm need entanglement. And we need entanglement gate to perform entanglements. So entanglement gates are very important. We will go into detail later. Now, some quantum gates has no classical counterparts. When I say classical counterparts, I mean those in your computer, right? For example, Hadamard gate, H gate. When I apply Hadamard gates to 0, it gives me a superposition of 0 and 1, right? You don't have this in classical computer because any register need to be either 0 or 1. You cannot say maybe 0, maybe 1. That is an error. But in quantum computer, we have this. So when you apply Hadamard gate to 0, it becomes 0 plus 1. And this one, for this state in general, we also call it the plus state, right? This is again the cat notation. It is just a symbol. And this is the plus state. When you apply it to 1, then it becomes 0 minus 1, and this is the minus state. And this is the minus state on the broad sphere. Okay, so that is the basics of quantum gate. Let's spend some time. Let's do some math to understand what a CNOT gate is about. Okay? And I will repeat again later. But however, this is a very important concept. I think it's good to learn. Now, first of all, this is a symbol, right? I put it here, U exclusive OR, which is just the CNOT gate. It is applied to 2 qubits, and we have a we call this control qubit, and then we have B, we call this target qubit. What does it do as a control qubit? What it does is that if your control qubit after this gate, you don't change. You are still A, nothing change. But B is going to change. The target qubit will change. It becomes A exclusive or B. But another way to understand this is that B will become its negation if A is 1, right? Because if A is 0, 0 exclusive or B actually is still B. But if A is 1, 1 exclusive or B becomes not B. Let's look at this example. When exclusive, this applies to 0, 0. The control qubit is 0. Control qubit doesn't change, so it's 0. But because it's 0, you don't do anything to qubit. So it is still 0 because 0 exclusive is 0. So this does not change, still 0, 0. But if it is 0, 1, control qubit is 0, then you apply nothing to 1, right? So 0 exclusive of 1 is still 1. So again, you see that when the control qubit is 0, then do nothing to the target qubit. Now, but when control qubit is 1, then you will do 1 exclusive or the target qubit, and target qubit is 0. So it becomes negative and not 1. 0 becomes 1. So 1, 0 becomes 1, 1. Similarly, 1, 1 can think in this way. Control qubit is 1, so you apply NOT gate to 0. You apply NOT gate to 1, so you become 1, 0. And that is the control qubit. So we define a quantum gate by talking about how the gate will change the basis states. Remember, let me emphasize again the basis state. Basis state are the classical state. You will see this in classical register. For 2 qubit, you have 0, 0, 1, 0, 1, 1, 0, 1, 1. 3 qubit, you have 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. So this defines how the quantum gate works. How about the general state? As we said, it is linear. So if you have a general state that is alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1, after you apply the control NOT gate, and this is the symbol of control NOT gate, then you will be equivalent to applying the control NOT gate to each of these. 0, 0, no change. 0, 1, no change. 1, 0 becomes 1, 1. And then, becomes 1, 1. So that's why gamma becomes here, because it's gamma 1, 1. It was gamma 1, 0. And then 1, 1 becomes 1, 0. Delta 1, 1 becomes delta 1, 0. That is how a control NOT gate affects a general two qubit gate. They are not in entanglement yet. Later, I will show you how to use control NOT gate to create entanglement. So here is the example of entanglement. Now look at this. I have 2 qubits again. At the beginning, they are at 0, 0, right? Because put them at ground state. So what I'm going to do is apply a Hadamard gate, right? If you forgot, this is the Hadamard gate. What do you do? Hadamard gate applies to 0, becomes what? Do you remember? Becomes a superposition of 0 and 1, right? Let me show you again. Hadamard gate applied to 0 becomes superposition of 0 and 1. So, but it only applies to the top qubit, which is A. So you see that after Hadamard gate, B is unchanged, but the top qubit becomes 1 over square root 2, 0 plus 1. It is in superposition. Now, I did not write here, but actually this is a tensor product of two systems. 1 qubit here, 1 qubit here. The first qubit is 0 plus 1. The second qubit is 0. And for tensor product, it's just like a regular multiplication. You can multiply it through the distribution law. So this becomes 0, 0 plus 1, 0. So this is the state of the whole system. But now we put it into a CNOT gate. This is the control NOT gate, if you forgot, that we just discussed. The control NOT gate will apply to both states, right? Let me remind you, although I write it separately, this is just 0, 0, and this is just 1, 0. And if you remember, for 0, 0, do nothing, because the first qubit is 0. But for 1, 0, you need to apply NOT gate to the second one, so it becomes 1, 1. As a result, 0, 0 is still 0, 0, but 1, 0 becomes 1, 1. And do you remember? This is the entangled state. This is just like what we said earlier, 1 over square root 2, for example, as spin up, plus spin down, spin down. This is the entanglement, right? So here we created an entangled state, which is very important for many quantum computing algorithms. We use Hadamard gate and entanglement gate. So good, I gave a basic introduction of quantum gate. Here I also want to talk about some aspect of quantum circuit. On the left, you see a classical gate. I hope that you all have learned the basics of classical logic. If not, you just trust me. This is something called LAND gate. If I tell you the output is 1 and the gate is a LAND gate, do you know what the input is? You don't, because 0, 0, 0, 1, and 1, 0 all give me 1. So this is not reversible. In our classical computing, they are irreversible. Okay? They are irreversible. So they consume energy. But for quantum computing, they must be reversible. Actually, quantum computer itself, the qubit operation does not consume energy. Okay? Quite contradictory, right? But we need a lot of energy to cool them down and to do readout operation. Other than that, when they do operation, they don't consume energy. So there's no heating problem. For example, this is a CNOT gate. If you say the output is 1, 1 and the gate is CNOT gate, I know the input must be 1, 0. This is easy to understand. Remember I talked about the broad sphere? What is a gate? A gate is just to rotate a state on the broad sphere or in its hyperspace. So if I can rotate in one direction, I should be able to rotate back in another direction, right? Just like an aeroplane, I can go from San Jose to Hsinchu. I can also go from Hsinchu to San Jose through the same path if there's no energy loss, right? So as a result, a quantum state is just a boring qubit sitting there. For example, electron. And then you apply a quantum gate. What is that? A microwave pulse or a laser pulse, right? And then it will change the state. apply another quantum gate, it change again. The qubit is still there. You don't need a large area for it. And anytime you can come back if you apply an inverse gate because it's reversible. So this is the flow of time, not space. In some algorithm, they might say they need 1 trillion quantum gates. Oh, that is a big deal for classical integrated circuit. But for quantum computer, no. We just need to apply 1 trillion laser pulse. Of course, whenever you do measurement, the wave function collapse to the basis state, then it's no longer reversible. Okay. So I think you might get tired. Okay. Okay. So now, actually, the question he just asked is related to what we are going to talk about. Now, as you can see, the whole quantum gate process, quantum computing process, is the rotation of the states on the Bloch sphere. So if I don't rotate exactly, right? Just now I say I fly the aeroplane to Hsinchu. If I just like land on Taipei or land on Taichung or just a little bit off, not on the airport, I did not have 100% correct gate. You always need infinite position. And this is error. This is just like analog, right? And the error can propagate because after that I want to fly to Tokyo. And because I land on Taipei, then I fly to Tokyo will give me even more error, for example, right? So error correction is very important. But just like what we just discussed, you cannot do error correction easily because in classical computer or communication, we use repetition code. For example, I want to send 0, I can send many zeros. If there's error, maybe it becomes 001, then by counting how many 0, I use the majority vote. I know that it is 0. Like if I call my parents, I tell them when I'm going to go back to Hong Kong, for example. They may hear July 15, but actually I was July 14 or July 16. Then I repeat 16 many times, July 16. They sometimes still hear 14, sometimes still hear 15, but most of the time they heard 16. They will say, okay, yeah, you are coming home at July 16, right? That is so-called repetition code. However, in order to do repetition, you need to copy the information, but you don't know the information most of the time, right? You don't know the most of the information at the time, right? So how do you copy? You need to do measurement. In classical computer, you can measure it. Oh, this is 1, then I copy 1 100 times. Oh, this is 0, I copy 0 100 times. But as we just said, in quantum mechanics, when you do measurement, it will collapse, right? It will collapse from alpha 0 plus beta 1 to alpha 0 plus beta 1 to either 0 or 1. Then how do you know whether it's 0 or 1? Right? So you cannot copy doing measurement. Then you may say, well, maybe I can come up some very smart quantum gate to do the copy. But unfortunately, there's something called no cloning theorem. You cannot copy arbitrary state if you don't know the state. Okay? So error correction becomes very difficult. And at the very beginning, before Shaw come up with his error correction code, people didn't care about quantum mechanics that much because they think that it's going to have a lot of error. You cannot correct that. But what quantum computing does is that they use entanglement and syndrome measurement to do error correction. For example, this is a qubit that contains the information I want. Maybe this is psi equals to alpha 0 plus beta 1. I cannot measure it, but I can make it to entangle with other qubit. This is a control NOT gate, as you remember. Now, if there's some error in this channel, I can do some measurement, but the measurement will be on this so-called auxiliary qubit or ancillary qubit. They are not important for the algorithm, but they are important for me to know what happened to this qubit. After this measurement, based on the output, then we'll apply the correction to them. I will give you an example soon, right? But the main point is that you try to entangle something with another things. While you cannot do measurement on this qubit, you can do measurement on another qubit. Okay, so let's take a look. This is something called the bit flip code. It's simplified, but it's interesting to understand. How many qubits do we have here? We have 3. The first one is alpha 0 plus beta 1 at the beginning. The other 2 are at ground state. So at the beginning, it is alpha 0, 0, 0 plus beta 1, 1. Because this 2, 0, 0 belongs to this 2, 0, 0. What I'm trying to say here is that the whole system is alpha 0 plus beta 1, the whole thing, tensor product 0, tensor product 0. And this 0 is this 0, this 0 is this 0, it becomes 0, 0, go in, I have alpha 0, 0, 0, beta 1, 0, 0. Okay, so this is not an entangled state because I can factorize 0 out, right? So this is the beginning. Okay, now I apply the first CNOT gate to it. What does it say? It says that if this is 0, do not do anything to the second qubit. But if this is 1, put a NOT gate to it, so this will become 1. So you can see that this becomes 0, 0, and 1, 1. Similarly, I have a control NOT gate. This is a 2-qubit gate. It does not involve this qubit, only this one and this one. This is control qubit. When it is 0, what do we do? Do nothing because it's control NOT. So 0, 0 here, 0, 0 here is still 0, 0. But if this is 1, apply the NOT gate to it. Because this is 1, apply NOT gate to it. So it becomes 1, 1. Right? So this entanglement process create an entangled state. And now we have the information entangled with this 2-qubit. Now we assume that we have noise. And this noise flip our qubit. For example, it flipped the first qubit. So it go from 0 to 1 and 1 to 0. Now this flipping is just like we applying a NOT gate. Right? So we model the noise, model the error as if someone add a NOT gate to the first qubit. And that's why 0 becomes 1, 1 becomes 0. Okay, we have an error. We don't know what happened. We didn't know what happened, right? Because we cannot do measurement. But then we use another 2 entanglement gates, CNOT gate. When this is 1, what do? You apply a NOT gate to it, right? So because now this is 1, then 1, 0 becomes 1, 1. I also have the same control NOT gate, so this 0 also becomes 1. So it becomes 1, 0, 0 becomes 1, 1, 1. This is 0, so do nothing. So 0, 1, 1 still 0, 1, 1. Do you see that? Then, after measurement, this is a combination of measurement and correction, but let's just take it for granted. This is something called control NOT gate. You apply only the NOT gate if both of these are 1. Now you look at here. When you input to here, both of these are 1. So what will you do? You will apply 0 to apply NOT gate to 1, right? So 1 becomes 0. And then you have 1, 1 here, still need to apply NOT gate to 0, so it becomes 1, 1, 1. Now this state is what? you can do a tensor product, it becomes alpha 0 plus beta 1, but then the whole thing tensor product 1, 1. Do you see that? Because this is 1, 1, 1, 1, I can factorize it out. And I don't need this one. This ancillary qubit got destroyed. It's useless now. However, I recover my original state without looking at it. Because based on the measurement, I know that a NOT gate has been applied to the first qubit. And therefore, I apply a NOT gate to it to flip it back. Well, when you add ancillary qubit, you actually have more chance to get error because this ancillary qubit can get flipped also. And here we try to show you that even that happen, we can still correct it. Okay, and this is an example of bit flip code. This is not enough to correct all quantum error, right? But however, the theory say that if you can correct the bit flip error, correct the phase flip, which is a Z gate, and then you can correct every error, even the arbitrary rotation, which we will not cover here. I think this is something very interesting. I would like to spend 1 minute if you have any questions about this, because this is a good place to summarize what we have learned. Any questions about this bit flip code? It's okay if you don't have question, but please ask. Maybe I give you 1 minute. Okay, I assume it is clear. Good. So in this whole process, we have gone through the basics of quantum computing. We know superposition is important for quantum parallelism. Measurement is very strange. It limits our ability in many applications, but it's very important in many algorithms. And then entanglement allows us to do something classical computer cannot do. And more importantly, you help us to do error correction. So quantum computing looks like promising. So in the second part, let's go deeper to understand the meaning of quantum gate. It's not too difficult, maybe a little bit boring, but the goal is to introduce you a few quantum gates so you can appreciate them, and then later we can also look at a quantum algorithm. There are a few gates I want to talk about: the NOT gate, CNOT gate, Hadamard gate, phase shift gate, Z gate, and swap gate. We already covered some of them. Some of them will be just review, but I want to introduce the notation and the matrix, okay? And particularly to understand the tensor product of the quantum gate. The first thing is the NOT gate. As I said, what is a NOT gate? A NOT gate is a gate that you can find a classical counterpart. The definition, we always define it by how it transforms the basis state or the so-called classical state. If you don't look at this bracket notation, right, this is called bracket notation. It's just say apply NOT to 0, you get 1. Apply NOT to 1, you get 0. Done. Exactly the same as what you learn in classical logic. And of course, for a general state, if you apply NOT to it, you get beta 0 plus alpha 1. So this is the bracket notation, but I think it's good to also understand how to implement it as a matrix. For 1 qubit, I actually did not discuss what is the size for 1 qubit. The dimension, it is a 2-dimensional qubit space. Right? Let's do not discuss what is qubit space, but we just understand it is 2 dimension. Because it has the basis vector, it has 2, 0, and 1. So I can write them in matrix form. For example, I can write 0 equals to 1, 0. I can write 1 equals to 0, 1. When I say 1, 0, it means I have one part of 0 and then one part, 0 part of 1. Here I have 0 part of 0. I have 1 part of 1, right? Basically, this is just saying that it is 1, 0 plus 0, 1, right? Which gives us 0. And this one is just 0, 0 plus 1, 1, which gives us 1, right? So in general, I can also write a general state. For example, here, alpha 0 plus beta 1 is just equals to alpha beta, because this is 0, this is 1. Okay, is that okay? So with this NOT gate, we also can define the matrix of NOT gate. In this case, it is like a poly X gate, 0, 1, 1, 0. Because if you try to apply this to there, you will see that it will does the job. For example, 0, 1, 1, 0 apply to the general state alpha beta, right? Because this is alpha part of 0, beta part of 1. 0 times this one, 0 times alpha plus 1 times beta give me beta. 1 times alpha plus 0 times beta give me alpha. So it does do what a NOT gate is supposed to do. It flips these two coefficients. So NOT gate is pretty simple. It's just 0, 1, 1, 0. Now, we also need to learn a concept called unitary. Unitary means that U times is the matrix is unitary, means that itself times the self-adjoint or the Hermitian conjugate will give to 0. The Hermitian conjugate of this matrix is just the transpose. Let me remind you, U dagger is just equal to the transpose, means you swap the row and column and then followed by complex conjugate. So in this case, you swap them, it is still the same. You find that when you do the multiplication, it gives you 1, right? So in summary, this is just a review. All the quantum gates need to be unitary because they are reversible. And second, you define quantum gates by how they apply to the basis state. And you can also have a matrix form for quantum gate if you write the vector in the column form. And that is a NOT gate. Okay? But what if I have 2 qubits? What do? I have 2 NOT gates like here. Apply this NOT gate to first one, second NOT gate to the second one. Well, you can still use the bracket notation because we apply the 2 NOT gates, so it's going to make 0, 0 to 1, 1. So that's why I have alpha 1, 1. Going to make beta 0, 1 to beta 1, 0. This is 2 qubit NOT gate, not a control NOT gate, okay? This is 2 qubit NOT gate. 0, 1 becomes beta 1, 0. Then I apply NOT gate to 1, 0. Then it becomes gamma 0, 1, right? Apply to delta 1, 1. It becomes delta 0, 0 because both of them get NOT. And that is how we do the 2 qubit gate tensor product. But how about in matrix form? It's very easy. So this is the matrix of NOT gate. So it's 0, 1, 1, 0. This is for the first qubit. We also have the NOT gate for the second qubit. How do we construct the NOT gate for the 2 qubit system? We use tensor product. And the way we do it is just put this whole matrix into each element. So I still have 0, 1, 1, 0, and then I do the tensor product to each of them, and then I multiply into it. So it becomes 0 times 0. So all these 4 become 0. 1 times this whole thing, so it is 0, 1, 1, 0. 1 times this whole thing, 0, 1, 1, 0. 0 times this whole thing, everything is 0. Okay, so this is a 2-qubit NOT gate. Now, if I have a state, again, what's alpha, beta, gamma? It means that this is alpha 0, 0 plus, let me do it again, alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1, right? So you look at this matrix multiplication, this row times this column will pick up delta. This will pick up gamma. This times this one will pick up beta, because 0 times A, alpha is 0, 1 times beta plus 0 times the other, so you get beta. This will get alpha, right? So this one will become this one. Okay, and that is how you construct a 2-qubit gate using tensor product. It doesn't need to be both CNOT, NOT gate. It can be different gates, but that is how you construct the matrix of a 2-qubit gate. Any questions so far about the math? You can stop me at any time. I will just move forward then. How about control NOT gate? Well, we already know what is control NOT gate, but because it's so important, let me remind you one more time. Control NOT gate is a 2-qubit gate. You have a control qubit and a target qubit. You don't do anything if the control qubit is 0. So 0, 0, still 0, 0. 0, 1, still 0, 1. But if your control qubit is 1, you apply NOT to the target qubit. So 1, 0 becomes 1, 1. 1, 1 becomes 1, 0. You don't do anything to the control qubit. So what is the corresponding matrix? It happened, this is the corresponding matrix. It's diagonal at the beginning, but at the end, you swap it. Because as you can see, its function is to swap 1, 0 and 1, 1. Okay, so if you apply this to a general state alpha, beta, gamma, delta, alpha and beta doesn't change. Still alpha 0, 0, alpha 0, 1, alpha, beta, but then it swap gamma and delta. So it becomes delta gamma, right? And that is the control NOT gate. How about the Walsh-Hadamard gate? So Walsh-Hadamard gate has no classical counterpart. And for example, if you apply it to 0, it will become a superposition of 0 plus 1. Apply to 1, it becomes a superposition of 0 minus 1. So what is the matrix form? It is 1 over square root 2, 1, 1, 1, negative 1. Let's check if this is the case. Again, h applied to 0 means this is the h. 1 over square root 2, 1, 1, 1, negative 1. This is given, and we trust that is true. 1, 0 means 0, right? I hope those forgot. Remember that. 1, 0 means I have 1 part of 0, right? And 0 part of 1, right? So this is 1, 0. Then we do multiplication. 1 times 1 plus 1 times 0 give me 1. 1 times 1 times negative 1 times 0 give me 1. So I have 1, 0 and 1, 1. That's why it's 1 over square root 0 plus 1. For h applied to 1 is similar, right? But this time the vector is 0, 1 instead of 1, 0 because I have 1 part of 1. So this one multiply this is still 1 because the 1 times 1. But this one is 1 times 0 plus negative 1 times 1. What do you get? Negative 1. That's why you have 0 minus 1. Right? And again, we know this is equal to plus and this is equal to minus. So this is the matrix form of the Hadamard gate. We can also think it in another way as another view, right? But what we can do is also what we said here. H applied to 0 give me plus. H applied to 1 give me minus. You can think it this way. And that is exactly what we are doing. For example, alpha 0 plus beta 1 after Hadamard gate become alpha plus and beta minus. But you need to remember what is beta minus. Beta minus, what is minus? Minus is 0 minus 1 divided by square root 2. And plus is 0 plus 1 divided by square root 2. If I have two Hadamard gate, use the same logic. It's going to convert 0, 0 to plus plus, 0, 1 to plus minus, 1, 0 to minus plus, and 1, 1 to minus minus. It's just like transforming the coefficient, right? And it's a good practice if you don't get it yet. For example, when you see plus plus, what does it mean? It means 1 over square root 2, 0 plus 1 times 1 over square root 2, 0 plus 1, right? And this gives us 1 over square root 2. You just go through the regular algebra, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Interestingly, what is this? This is a superposition of all the basis states. And this is very useful in very many quantum computing algorithms, right? Do you see that these are the basis states and they have equal superpositions? We talked about entanglement gates already. I just quickly to remind you, right? To review one more time. So we have 0, 0. I hope at this point you are better now. 0 doesn't change. We apply Hadamard gate. You actually make this into a plus state. And this plus state is nothing, right? It's just 1 over square root 2, 0 plus 1, right? And then you do distributional, get 0, 0, 1, 0. In the control NOT gate, because the control qubit is 0 here, you put 0, 0. It is 1 here. Then you apply NOT gate to the second qubit. And then, so it becomes 1, 1. Okay, so that is just a review. Okay, so let me see how much time I have. Yeah. Now, I want to introduce another gate, which is called phase shift. Let's see what it does. As I said many times, a gate is defined by how it transforms a basis state. Here is a basis state 0. Phase shift gate phi means that don't do anything to it when it is 0. But when it is 1, multiply e to the power I phi. And we say that this is a phase shift because the magnitude of e to the power I phi is 1. The corresponding matrix is this one, right? We can quickly do a check. For example, UPS phi applied to 1 is just 1, 0, 0 e to the power I phi. And the vector form of 1 is 0, 1, right? And this gives us what? 0 because 1 times 0 plus 0 plus times 1 is 0, and e to the power I phi. And this is just your e to the power I phi times 0, 1, which is exactly equal to e to the power I phi 1. Right? That is this one. We use matrix to check it, right? So this is the correct form. Now, this is very important. You might think, what is the point of shifting the phase? Means multiply by e to the power something to the state. Because you use this to do a lot of constructive and destructive interference in the future. When phi is equal to pi, then what is that? It's e to the power I pi. It's cosine pi plus I sine pi, which is -1. Then the matrix becomes 1, 0, 0, 1. And this is the so-called sigma C matrix. And we also call it the Z gate. Earlier, I already mentioned that the NOT gate is nothing but also the Pauli sigma X matrix, right? And now we see the poly sigma Z matrix. They are very important in many, in the foundation of quantum mechanics and linear algebra, because the poly matrix and identity matrix form the basis of any Hermitian 2x2 matrix. Okay, maybe too much for you, but they are very important. You do quantum machine learning, variational quantum linear solver, variational quantum eigenvalue, or whatever. You need to decompose those Hamiltonian into the summation of poly matrix product. And just take this opportunity to talk about swap gate. Swap gate is important because sometimes you need to swap the states of the qubit so that you can bring the state closer to another qubit for entanglement, such as superconducting qubit. But anyway, what it does is very simple. You give AB, it gives you BA, and that's it. So what does it do? If your input is 0, 0, swap them, still 0, 0. 0, 1, swap them, become 1, 0. So beta 0, 1 becomes beta 1, 0. Gamma 1, 0 becomes gamma 0, 1. Delta 1, 1, still delta 1, 1. And this is the matrix, right? And now you may see that my computer is getting slow. Sorry, right? This and this are diagonal because this is 0, 0, this is 1, 1. We don't change it, but then 0 and 1, 0 are off diagonal. I mean, they're, I don't know how to say it. They're opposite, so they get swapped. Okay, and in general, this is what we have that I already discussed. Okay, so I have introduced some important quantum gates here. And do you have any questions? Let me just pause for 1 minute, right? If you have any questions. If no, then I will go ahead to go to part 3. Now I want to combine what we have learned so far. And please stop me anytime if anything doesn't make sense to you, okay? To discuss an algorithm called Deutsch algorithm and try to demonstrate the important concepts in quantum computing. Here we'll introduce a concept called quantum oracle and how to implement it. And I hope that you can see the power of quantum parallelism. In every quantum algorithm, the first thing you want to ask is, what is the problem I'm trying to solve? This Deutsch problem or Deutsch algorithm we are going to introduce is to find a function to check whether it's balanced or controlled. What is a Boolean function? It means that the input, the function, a Boolean value, 0 or 1. And the output is also 0 or 1. Now here we're looking at a very simple and useless problem, almost useless, but actually not necessarily useless. But it is like that. I have a function f. Now, the function can be so-called constant. What does it mean? When I input 0, it gives me 0. When the input is 1, it gives me 0, right? So this is a so-called constant function because it's always give me 1, 0, the same result. Or I can have another function. You give me 0, the output is 1. You give me 1, the output is also 1. This is also a constant function. Both of them a constant function. Now, there is another two possibility. The input is 0, output is 0. Input is 1, output is 1. The output has half 0 and half 1. That is called balance. Or the input is 0, output is 1. Input is 1, output is 0. It is also balanced. So we are only interested in knowing whether they are constant or balanced, right? We don't care their values. Basically, it is saying that I just want to know the properties of this function. I don't need to know their output. Okay? For example, I buy a car. You want to say, is it expensive or cheap? You don't care how much it costs. The exact value is not important. Is it more than my income or less than my income? Something like that. For this type of problem, we can use quantum computing. Now, if you use classical computer, how do you know whether this is constant or balanced? Remember, this function is a black box. You don't know what it is. It can take 100 years to compute, or let's say 30 years to compute. To know whether it's balanced or constant, what do you need to do? I need to put in 0 and see the output. Maybe I get 0. Then I put in 1, let it compute one more time. I can get 0 or 1. If it is 0, I say, oh, this is a constant function. And if this is 1, oh, this is a balanced function. Correct? So classically, for this simple problem, I need to compute 2 times. But for quantum computer, I only need to compute 1 time. I can use quantum parallelism, which I'm going to show you. So originally, I need 60 years to find out the answer. Maybe I have died already. But now, use quantum computer, I only need 30 years, right? Of course, this is still not a good example, but just want you to understand the argument, right? So this is the problem we are trying to solve. How do we compute it so fast with quantum computer? Before that, okay, I also have the QR code. I'm going to send you slides later. You can look at the details on the video. Before that, let's understand something called quantum oracle. Quantum oracle is the central part of many quantum algorithms. The most important thing is that it needs to encode the function, the problem you are trying to solve into the oracle. It is nothing but just a quantum gate. A very big quantum gate. Okay? Not the regular quantum gate we just seen, right? It's a quantum gate with the information of the problem. And that is how it works. And when you apply the quantum oracle to xy, let's just think about 2 qubits. The output will be x for the most significant qubit, but for the least significant qubit, it becomes y exclusive or f of x. So you see that you should be able to compute y exclusive or f of x, and f of x and is the problem you try to solve. And that's why I say it encodes the problem in the quantum gate. But look at this, you lose the information because you are not computing f of x. You are computing y exclusive or f of x. So you need to find a smart way to get the information from there. Okay? Now let's take an example. Let's say it is a constant function. So if it is a constant function, what does it mean? It means f of x always give me the same thing. Here I assume it is 0. So it means f of 0 equals to 0, f of 1 equals to 0. That is the case here. F of 0 equals 0, f of 1 equals 0, right? Assume this is the case. Let's see what this quantum gate, which is quantum oracle, does. If your input is 0, 0, again, based on the definition, the first qubit won't change. So 0, 0, 0, 1, 1, 0, 0, 1, it doesn't change. But the second qubit is going to be y, which is this one, exclusive f of 0. So let's look at it carefully. This is x, no change, 0, 0, 1, 1. And then you will put y here, so 0, 1, 0, 1, 0, 1, 0, 1. But each of them exclusive f of x, which is f of 0, 0, 1, 1, f of 0, 0, 1, 1, right? So this implement x, y exclusive or f of x. Now, do you remember what we just said? F of x equals 0, right? It's constant function. So all of these are 0. So they are 0, 0, 0, 0, right? So the result is 0 exclusive of 0 is 0, 1 exclusive of 0 is 1, 0 exclusive of 0 is 0, 1 exclusive of 0 is 1. And in this particular case, it does not change the input. This is just an example to tell you what a quantum oracle can look like. The most important thing is that we need to encode the function that we want to solve into a quantum gate. Now, how to do it can be very difficult. And you also need to be careful that if you take exponentially more time to construct this quantum oracle, then your quantum computer becomes useless. So what is the Deutsch algorithm? How does it solve it? First, we construct the quantum oracle by incorporating the function into the gate. So this is the quantum oracle. We will prepare initial state, which is a superposition state. We have 0, 0, go through the NOT gate, becomes 0, 1, right? Because this becomes 1. This is a NOT gate. Then we go through Hadamard gate. 0 becomes plus, 1 becomes minus. Remember? So that's why our initial state is plus minus. But we can express it as 1 over square root to 0 plus 1 tensor product 1 over square root to 0 minus 1. Then we put this into the quantum oracle. And I hope now you understand why it is faster. Because we prepare both 0 and 1 plus and minus. They will receive the quantum oracle function, which is this one, at the same time. And that is the quantum parallelism. Now, but this one was constructed very carefully. If the function is constant, after this quantum oracle, it will become plus. If it is balanced, it will become minus. Okay, but we do not measure plus or minus. We apply a Hadamard gate, then convert it to 0 and 1, and we do the measurement. So maybe a little bit confusing now. I still have my final slide, and let's discuss how it works. We don't see all the math, and don't worry, I just want to show you the philosophy, right? You can go to my book. I think it should be downloaded for free at your school, or use the YouTube link I send you. But I want to show you why this is a successful algorithm. Do you remember, as I said, you apply the quantum oracle to the plus and minus states. And plus minus states are just 0, 0, 0, 1, 1, 0, and 1, and 1, 1, right? So if we apply the quantum oracle here, I skip the step because of time. You trust me, you will get 0, f of 0, 0, negation of f of 0, 1, f of 1, and then 1, negation f of 1. Now, if it is a const, first of all, you see that it do the computation at one time. It compute f0 and f1, f of 1 at the same time. That's why you have this parallel operation. That is the first thing. But how do we extract the information? Because this is constant, so f of 1 equals to f of 0. F of 1 equals to f of 0. So I can write f1 of 1 as f of 0, f of 1 bar as f of 0 bar. Because of this, I can do factorization. Now I have f, I just rewrite this one, right? I take out the 0, 0, 1, 1. Now I factorize it. F of 0 factorizes out becomes 0 plus 1. F of 0 bar factorized out becomes also 0 plus 1, although this is negative. I have two 0 plus 1. They are just plus, right? The plus state. I take them out. Then it becomes plus state of f of 0 minus plus state of f of 0 bar. I factor it out. Do you see that the first qubit is plus? Now I'm going through a little bit too fast. You probably cannot follow. But my main point here is that first, we do parallel computation by computing f of 0 and f of 1 at the same time. That is first thing. Second thing, when they are constant, you will find that the first qubit will always be plus. Do you see that there is no negative component? The first qubit, this is 0. As long as your function is constant, the first qubit is always plus. It won't be negative, minus. Remember when we do measurement, the function will collapse to either plus or minus, the basis state, right? But now I only have plus. It always collapses to plus. So therefore, if we find it is plus, I know this is a constant function. Similarly, if it is balanced, now this time, because it's balanced, what do I have? I know that f of 1 equals to negative f of 0, right? So here is a little bit, I try to group them together, right? Because this is f0, okay? And f of 1 is just equal, bar is just equal to f of 0. F of 1 bar, right, equals to f of 0 because it is balanced. And then f of 1 equals to f of 0 bar. So this time I group them differently. When I group them, it becomes 0 minus 1, which is minus. So again, when I do measurement, it only has the minus state. So if I measure minus, then I know it is balanced. Okay, so in this process, we use some very smart algorithm, very smart way to do it so that first, it will do parallel computation. Second, if it is constant, you only get plus. If it is balanced, you only get minus. At this moment, you still don't know what is f of 0 and f of 1. You don't know. You did not, you compute it, but you don't know because quantum computing algorithm did not let you know. However, you know whether it's balanced or constant. Okay, so this algorithm show you the importance of superposition, right? Show you the importance of parallelism. It doesn't have entanglement here. However, it tells you the importance of measurement, right? And no obvious entanglement, right? But I hope this is a good starting point. And and I think I will stop here for today. Let me know if you have any questions. Next week, I will talk about the hardware. Part of the talk, as Professor Chung just said. And last time we have covered the quantum computing basics. We look at quantum gates, and we also try to understand quantum algorithm, right? The most important thing is to understand that quantum computing needs superposition and also entanglement in order to do something that classical computer cannot do. Although we cannot fully spend time on some difficult algorithm, but at least we appreciate the power of superposition and also entanglement. So today I will talk about superconducting qubit hardware and spin qubit hardware. We probably will have some more time, and then I will talk about the photonics qubit and also trapped ion qubit. The goal is to let you have a feeling of how quantum computers are implemented. So I will just go fast. And this is just a reminder about my book, right? Last week's class is somehow covered in this book, Introduction to Quantum Computing, which you should be able to download for free if you connect to your school's VPN. And then today's talk is mostly from this book, Quantum Computing Architecture and Hardware for Engineers. This book covers the superconducting qubit and spin qubit. Right, and I have another book coming up, but this is on archive. You can download for free also, which cover the trapped ions. Later, I will add photonic qubits and neutral ion qubit, and this is my YouTube. I need to fast forward. Sorry for that. Should be quick. This what we discussed last time on the basics. We talked about error correction, right? We talk about different type of gates, and then we talk about the algorithm. So now I will talk about superconducting qubit. Now I will spend more time on superconducting qubit because here also give us an overview of the quantum computing architecture, and we try to go deep to understand how it works, how it fulfills the criteria. So feel free to ask questions in this process. I treat this more like a tutorial. There will be a lot of math and physics. You don't need to worry about that if you have not studied that before or learned that before. It is fine. We just want to have a feeling. And if you want to go deep, you can go to my book or just any YouTube or whatever. Probably can help you well. Okay. So first, what is a quantum computer? What type of hardware can be used for a quantum computer? For example, can I use a spinning coin to do quantum computer? Right? Last time we say spinning coin can be used for a classical computer, but it cannot be used for a quantum computer. Right? So there is a criteria called DiVincenzo criteria. This is the necessary criteria. Okay, that if you want a technology that can be used to make a quantum computer. The first is that you need to have a scalable physical system, that it has two well-characterized levels. This is very important because we already said last time, for a quantum computer, we work on two levels, state 0 and state 1. And of course, we can then have the superposition of state 0 and state 1, right? So this needs to be a quantum system that allow superposition, but you also need to have a two-level subspace. Can I have three levels? No, depending on how you define your algorithm, right? For example, now we only assume it is a qubit system, then it can only have 0 and 1. You cannot have 2, 3, 4. Okay, so you need to be well separated and well characterized two-qubit system. Two-level system. Then the next thing looks very strange, right? Is that we should be able to initialize the qubit. What is the meaning of initialization? It basically saying that I should be able to put the state to 0. And if it is at 0, I also need to keep it at 0. In classical computer, it's very trivial, right? To have initialization, I just put 0 to the, let's say, the memory or register, then they are 0, right? But in quantum computer, because it's so subtle and it's quantum mechanical, you need to be able to initialize it with high fidelity. And the time is also important. If you take 1 year to initialize it, that is a problem. That is because many algorithms needs initialization. And it not just initialize at the beginning. Sometimes in some algorithm, we need to initialize at the middle of the algorithm. So the initialization should have high fidelity and also within a reasonable time. We will not discuss this in detail because it's rather trivial, although it's not trivial to have a high fidelity. But there are two ways. One is thermal. That is easy to understand. If you are at excited state, you just wait. It probably will lose the energy and become zero state, right? Another is called active reset. What you do is that you do a measurement. If it is 0, then you apply a pulse to make it, if it is 1, you apply a pulse to make it 0. If it is 0, then you do nothing. Then by doing that, you initialize all the qubit to 0 state. The third criteria is easy to understand. You need to have a long decoherence time. As we know that quantum object, last time we mentioned that they may lose its states, right? You may go to dephasing or you may lose your energy. So they need to maintain their state for a long enough time so that you can have enough computation. Now, some of you may say, we might have quantum error correction. Why this is important? This is still important because quantum error correction only works if you have a long enough decoherence time, which translates to the error of the qubit and the quantum gate. So a long decoherence time will reduce the resources for error correction also, right? So this is still very important. Fourth, you need to be able to form a universal set of quantum gates. What does it mean? So in classical computer, if you know, right, in classical computer, we can decompose any circuit into, let's say, for example, NOT gate and OR gate, right? Any complicated circuit, every circuit in your iPhone, in your laptop, can be decomposed in NOT gates into NOT gates and OR gate. We have something similar in quantum computer. You need to be able to make one qubit gate. That means it operates on one qubit, and also be able to create an entanglement gate. So last time we spent quite a lot of time to talk about entanglement. Entanglement is very critical. So you should be able to do entanglement. And that, of course, is a 2-qubit gate. So if you can do that, then any quantum circuit can be approximated efficiently, okay, with low error, with a universal set of quantum gates. So therefore, later we will try to see that the architecture I'm going to show you, they can do 1-qubit gate, they can also do entanglement gate. Now finally, this one again for classical computer is trivial, right? Measurement. You should be able to measure it, and more importantly is on the specific qubit. Last time when we said when you do measurement, what happened? Wave function will collapse. So you cannot let every qubit collapse in some algorithm. You want to selectively measure some qubit. So your architecture should allow you to specifically select some qubit to do the measurement. That is very important. For example, in quantum teleportation, right, you will see that you will only measure one of the qubits. So again, 5 criteria. 2-level system, able to initialize it, long decoherence time, you have a set of quantum gates, universal quantum gate, a universal set of quantum gates, and also you can do specific measurement. So we will study this in the coming slides. Now, these are just the necessary criteria. But if you want to have a large-scale quantum computing, you should have some feasible inter-chip quantum communication. You should be able to integrate that, right? The layout should also be compatible with error correction. We will not discuss this much, but please bear this in mind. Okay? So the first thing, if you want to bring home for this slide, is that you recognize something called DiVincenzo's criteria when you want to define a quantum gate, a quantum computer. Okay, now I do have reference. Last time I showed you, it is at the end of the slide. I can send the slide to Professor Chang later, and he can share with you. Now, let's take a look. What is a quantum computer, right? Now, again, it is just some passive physical qubit, This is a quantum object, right? Maybe superconducting qubit, trapped ion, spin qubit. You have some of the physical qubits standing there. They are very boring. They are passive. They don't do anything. And what we do in quantum computing is that we send an initialization pulse to initialize the qubit. We then send some gates, pulse, which are quantum gates, to manipulate the qubit, to change their state. And then we may read out, right? And we need to have a well-defined two-level system. It may interact with the environment. It can lose its information. And these are the scenario of a typical quantum computer. Now, this is not the case for photonics, however, right? But this is still a good picture to memorize it. And we want to form universal set of gates, which means, for example, I will be able to have identical phase shift gate. I will be able to do rotation about x-axis, y-axis, z-axis of the broad sphere. Last time we talked about broad sphere, right? And then here is entanglement gate. This is the CNOT gate. If you forgot, this U exclusive OR is just the CNOT gate, okay? This is another set where you can have the Hadamard gate, S gate, and T gate, and the CNOT gates. Then this will form an universal set of quantum gate. So you see, quantum computing is nothing. It's just that you send the right pulse with the right frequency, right shape, right amplitude, right phase at the right time for the right duration. Okay, so it is like you have the algorithm, you keep sending the pulse, and then you manipulate the object, eventually do the readout and get what you want. So this is just like a well-organized physics laboratory. Maybe 60 years ago, an atomic physics lab is the same as this, but it has a lot of wire, a lot of human-tuned laser, but now they are all in a well-orchestrated way. Okay, so that is what a quantum computer looks like. Now let's start with superconducting quantum computer. This is the same. Now here, what I'm showing you is a typical superconducting quantum computer. You see that at the bottom, I have a chip. This is just like a regular IC chip. At the top, at the room temperature, I have a bunch. Here we call it Quantum Machine is a company that it has this system, but you just treat it as a Python programming with FPGA, with ASICs, with a lot of special IC that you can program them to generate some pulse. Remember, I just mentioned that quantum computing is nothing, but you just send some pulse to the qubit. So this pulse will be promoted to higher frequency through the so-called mixer and oscillator in microwave circuit. And this is at room temperature. So it can be very bulky, it consumes a lot of energy, but it's okay. It's at room temperature, you can cool it down. The signal will go down through a dilution refrigerator. It has many stages. It has a 4 Kelvin, 700 millikelvin, 10 millikelvin stage, right? So the signal will keep going down. We have the attenuator. This attenuator is to reduce the thermal noise, right? The goal is that at room temperature, you have a lot of thermal noise, 26 millieV, and this will get attenuated. So when you reach this quantum chip at 10 millikelvin, this noise becomes very small compared to the quantum noise. So in this chip, if we blow up, it is just a transmission line. Again, this is just a waveguide, microwave guide, which we use in microwave engineering. Eventually, it reached this one, what we call a transmon qubit. So what is a transmon? Basically, this is a capacitor. And then here we have something called Josephson junction, which we will discuss later. It's a very, very simple circuit. Just a junction, which is almost like a capacitor in parallel with another capacitor. And that's it. This is 1 qubit. So how do we do a qubit operation. We send the microwave pulse. It go through this transmission line, and then it interact with the qubit. Then the qubit state will change. Then you are done. This is a 1 qubit gate. Now, what if I want to read out the state of the qubit? I will also send a pulse, but at different frequency. You see this local oscillator is at 7.2 gigahertz, and then we keep going down. It will go to the chip, but then it will also have a refraction. This refraction will then go through here, and then we have an amplifier, go through another amplifier, and then eventually you will get some signal. And then we will use signal processing, including machine learning, to distinguish the signal and to determine whether the qubit is at 0 or at 100 or at one state. So you see that in this whole process, everything is classical. It's just microwave engineering. The only two quantum object is we have a qubit here. This is the qubit, right? And we also have an amplifier called traveling wave parametric amplifier. This is a type of quantum limiter amplifier. What it means is that this amplifier will add the least amount of noise when you amplify the circuit. For those amplify the signal. For those who have learned microwave engineering, you probably know that there's something called noise figure. But it's not difficult to understand. When you amplify a signal, you amplify the noise also. So the signal to noise ratio is not changed. However, your device will inject new noise to it. So actually your noise to signal noise ratio will reduce. But quantum limiter amplifier will add the least amount of noise, or in other words, it has what we call the least noise figure. It deteriorate the signal to noise to ratio the least. And after that, they keep amplified by other regular amplifier. Okay, so here I show you again what is a superconducting quantum qubit system look like. You have the 1 qubit gate, just microwave pulse. Readout pulse, we try to sense how it change the refraction. We will discuss more, and that is what a superconducting qubit system about. Feel free to stop me if you have any questions. Okay, so now we start look into more details, but don't worry about the equations. First, remember we say the first DiVincenzo criteria is that we need to have a two-level system, not 2 qubit, a well-defined two-level system. Now, how we do it? We do it by having something called Josephson junction, which is shown here. Okay, it is abbreviated as JJ. If you look at it carefully, it is just a capacitor, except that we cool it to a very low temperature, so it becomes superconductor, insulator, and superconductor. Okay, but still a capacitor. However, because it is a superconductor, the electron here will form Cooper pairs, and they become a macroscopic quantum object. All the Cooper pairs will condense, what we call it Cooper condensates to the same state. We'll call it Cooper pair condensate, and they are described by one single parameter, which is the phase. The phase difference across these two Cooper pairs or two sea of Cooper pairs will change the characteristic, and due to the tunneling between them. Okay, but we won't go into detail. The most important thing is what? It turned out that it has inductance, and the inductance is also non-linear. So it's just like a regular inductor, but it has a nonlinear part. And this is very important. So what I'm showing on the left here is a Josephson junction. This is just like an LC tank. So if some of you has learned the elementary circuit, you know that if you have inductor and also a capacitor, you have a resonance frequency, right? You have an omega naught, you have a resonance frequency. If you cool it down to very, very low temperature, you basically can quantize it. So this one will jump a little bit. If you have not learned second quantization of the of an electric circuit, it will be a little bit difficult to understand. But just trust me, this is just like a simple harmonic oscillator. It will have this potential profile where this is the phase and this is the energy. This is the phase difference across the inductor or the Josephson junction. And it will give you even spacing of the level. You will have 0 here, because after quantization, you can have either 1 photon, 2 photon, or 0 photon, 1 photon, or 2 photon occupying in this LC tank. This is not good because, as we said earlier, we don't want to have the equal spacing, because if it is a LC tank, you actually will quantize the level to here for, let's say, for E21, right? So you might have this level, and this level. As a result, remember what is a gate? The gate is a microwave pulse. You apply the energy, then its state will go from here to here. And then you apply one more, it might go to here instead of coming down. Then you don't have a well-defined two-level system. And that's why Josephson junction is used, because it has a non-linear inductor. Okay, so when it is non-linear, it gives you this profile. So let me just emphasize, this one is for a regular LC tank, but this one is the Josephson junction plus capacitor, which is what we have here. Now this is non-linear. As a result, when you quantize the level, you may have 2 levels here, but the third level will be lower than what you have if you were an LC tank. And now you see that the energy between 0 to 1 is different from 1 to 2. So if you apply a pulse to it, you will only change between 0 and 1. So this gives us a well-defined quantized level. So this is how we encode a superconducting qubit. So this is already simplified. There are many other type of there are different type of Josephson of a superconducting qubit, but this is a simplified one. The most important is that you should understand we use Josephson junction to replace an inductor because it has non-linear inductance. And then we have a well-defined 2 levels. And the level is depending on the type of Josephson junction. It has different meaning. Some of them means that you have an extra pair of Cooper pair, another or you don't have. Okay. Now, I also need to introduce another qubit which is important in, you will see in the literature when you talk about superconducting qubit. Now, we just say that the 0 and 1 level is just like the omega 0 in a regular LC tank. And if you remember, this is just 1 over square root LC, right? That is the angular frequency. That is the qubit energy. So after fabrication, as we said, this is nothing but just a circuit, right? You fabricate it, and then you have a fixed qubit frequency. And that is not good enough for application. So people also come with something called first tunable qubit. So what is a flux tunable qubit? We again will not go into detail, but the point is that if you have learned superconducting electronics, you will find that the flux, magnetic flux, passing through a closed loop needs to be quantized. Okay, it means that it can only have 0, 1, or 2 or 3 amount of the quantum flux. This one, flux quantum. Okay, if you have not learned this before, it is fine, but just trust me, it need to be quantized. Similarly, if we try to put the two Josephson junction in a loop, okay, this is a two Josephson junction, connect them together. This one need to obey certain quantization criteria. Not the same, it does not say that it need to be some unit number of this, but the it's going to, but you need to follow some rules. But more importantly is that this one, if we have different flux going through this route, the effective inductance will change. Okay, so effective L will change, right? Changes depending on the external flux. So if I add a magnetic field, I change the strength of a magnetic field, this one will have a different effective inductance. So you remember, Josephson junction is used to provide the inductance, and thus you have a certain qubit energy. So here, by changing the flux, I will change the effective inductance. Of course, it also have the corresponding Josephson energy. Okay, so maybe I won't go into this, but the point is that it changed the inductance. So this is the so-called flux tunable qubit. So this shows the schematic of a possible layout. So what we have here is a current bias line. So if you pass the current into this bias line, then what will happen? We know that you are going to create magnetic field, right? Around this current, right? Now, we also have two Josephson junction here. So here from the loop, you see that it's just like having a loop. So if I change the size of the current, the magnetic field will change, the flux will change. As a result, I change the effective inductance, and of course, the result is I also change the qubit frequency, omega 01. Okay, so we did not talk too much about physics, but the point is I want you to understand how we change the qubit frequency if you already fabricated a chip. Okay, so we have a two-level system. It will be useful also to see how we usually fabricate a Josephson junction. It turned out that the quality between this aluminum oxide and aluminum, again this is the Josephson junction, is very important. So what people will do, usually there are two old methods called Dolan-Bridge or Manhattan method. Let's only look at this Dolan-Bridge, right? So you have some mass which is suspended. So what we did is in this y direction, in the direction into the screen, it actually has an anchor. This is just like a bridge. Okay, the bridge hanging over over the screen, right? So this go into the screen and go out of the screen, and then it anchor there. So we do some directional deposition. The first time we deposit aluminum, so we have this aluminum here and this aluminum here because it's depositing in this direction. And then we do oxidation. So in this process, you will form this oxide. I should actually also draw oxidation to here, but I did not draw it. right? So we have oxidation, and we continue. We don't break the vacuum. We also do another angle deposition. This time, because of this mass, it will deposit to this region and also to this region. So with this, I form a Josephson junction, and these are useless. They will just live there. And then we remove the mass, then we form a pretty high quality Josephson junction. There's another way called Manhattan Bridge. I won't cover it because of time, but you can read my book about that. Okay, so that is how we fabricate a Josephson junction. Now we say that also the decoherence time of a qubit is also very important, right? We want it to be long enough. So there are two types of decoherence time. The first one is the so-called T1. What is the meaning of T1? Is the FH time 1 will decay to 0. So what we do here is to do a measurement. So we put the qubit to 1, and then we wait for some time. Then we measure it to see whether it's at 0 or 1. And remember, whenever you measure it, it will collapse, right? So if you measure it immediately, you're supposed to have 100% of chance to get 1. If you wait for some time, maybe you only have 50% of chance to get 1, because 50% of them has decayed to 0. Right? We can do many identical copy and do the measurement, or just repeat the measurement many times, right? And so you see that it decays exponentially for the probability to get 1. So you fit this equation, and then you find out that its characteristic time is about 222 microseconds. So this is the typical decay time, is about 100 microseconds. This one is a relatively long. Okay, which is okay because the gate time is about 200 nanoseconds. So in that case, you can perform quite a lot of operation before it loses the energy. So that is the T1 time. Now, it also has the so-called T2 time. So what is the meaning of T2 time? T2 time basically is related to if you have a qubit in the alpha plus beta 1. How long will it take to lose the information between alpha 0 plus beta 1 becomes something I don't know, 0 plus I don't know 1, right? So it means that it loses its phase information. If you remember when we talked about Deutsch algorithm last time, we need superposition. We need interference to cancel out some of the superposition term. If the phase is lost, we will not be able to do the computation. I will not go into the details how to generate this plot. I can quickly say that we bring it into superposition and then let it wait for some time and bring it back, and then we try to do measurement. But basically, the envelope of this shape contain the characteristic time of T2. This is proportional to e to the power negative t divided by T2 star. Okay, so a longer T2, right? Well, longer T2 will actually make this larger, so you will decay slower. Okay, so that is the decoherence time. In this particular quantum computer we were using, is about 40 microseconds. So T1 time usually is because you lose the energy directly to some energy absorber, for example, some two-level system or some defects that resonate with your qubit frequency. And this one is like you lose the phase due to the interaction with the external environment. So here I would like to talk about the so-called two-level system. This is an important topic in superconducting quantum computer now. So why? Because it's limiting the lifetime or the decoherence time of the superconducting qubit. Basically, it is like all the defects So because here you see the metal, and here is the substrate. They can be silicon, or they may have silicon dioxide, sapphire, or other amorphous material. So they have a lot of defects, like what it is shown here. Now, this defect is very interesting. They are actually just atomic or ionic structure. So, for example, you may have something like this. This is an atom or ion, but they are defects. So it can go from one state to another state like this. So this atom or ion can move to here, but it is just like when you're flipping a foil, right? You need to apply energy to flip them because there is a barrier between them. So if I call this A, I call this B, this might be the A, this might be B. So what you're saying that is A state, it has a low energy. At B state, you also have a low energy. To go from A to B, you need to go through a high energy state because when the atom is at the middle, it actually doesn't have the lowest energy. Now, if it's just room temperature, you will be able to overcome the barrier easily. But at very low temperature, it won't because it doesn't have enough thermal energy. However, the atom or ion can actually tunnel through this barrier. So this is a tunneling effect. So it's an ionic tunneling model. And this becomes very important at very low temperature, which is the temperature at which we have this superconducting qubit. Okay, and people start able to visualize them by doing some very clever scanning microscopy, spectroscopy, right? So in summary, maybe this is some of you might not have learned this before. This is more in material science, but the point is that the two-level system, which is due to the defect moving on the amorphous surface, limits the T1 and T2 time of a superconducting qubit. So how to reduce this is very important. For example, if you can reduce the electric field, that will make the effect less. And people indeed have tried to increase the gap between the plates so that there will be less electric field. Okay, now I will talk about how to do one qubit gate. Again, there's a lot of math we cannot cover, but my goal is to tell you this. First of all, I have a qubit here. Remember, I have a Josephson junction, and I also have a capacitor. So this is a qubit. It is boring, it is sitting there. How do we control it? Which is just an electrical circuit. We couple it through to a voltage source through a capacitor. So in this voltage source, we will generate some very complicated waveform. We have an envelope function. This is the envelope function. And then times sine of a certain frequency with a certain initial phase. Now, if you try to solve the circuit, go through the circuit quantization, what we call circuit quantum electrodynamics, you will get this equation. But you don't need to understand if you have not used that before, right? In my book, I go through step by step if you're interested. But the most important thing I want to point out here is that this is the so-called interaction Hamiltonian, which determines how the qubit will change as a function of time. Okay, just trust me. The qubit will change as a function of time. I think you will agree if we apply a pulse to it. Just like you push a car, the car will move. It will change. How it changes, depends on Hamiltonian, based on Newton's law. Here it depends on a Hamiltonian based on Schrödinger equation. But doesn't matter, it will change. The important thing is that this Hamiltonian contains sigma z, sigma y. If you do a transformation, it will contain sigma x, sigma y. Again, you don't need to understand what it is. But what you say is that this determines how it rotates about the y assets on the broad sphere. We discussed last time. So I think I should have make the broad sphere here, but I think I can just go back to show you what it is about. We did not study too much at that time, but this is the broad sphere, right? It contains the states on the broad. Every state is a point on the broad sphere, and I told you last time already, a gate is just a laser or microwave pulse. Now, if I have a sigma y, it will rotate about this axis due to sigma y. If I have a sigma z, it will rotate about this axis. If I have a sigma x, it will rotate about this axis. And the point is that if you can rotate about any of these two axes, then you will be rotated from any point to any other point. Okay, so this is important. So let me go back to the superconducting qubit. I try to say is that if you go through the difficult math, eventually you have a Hamiltonian like this. You see that I have sigma y, I have sigma z. If I do a so-called rotating frame approximation, which I do not cover here, you also have sigma x. So basically, I can rotate the qubit about broad sphere on any axis. How fast, how much it rotates depends on what? Depends on the coefficient. And what are these coefficients? Look at this. H bar omega r depends on what? The total capacitance. Depends on S of t. Okay? And it also depends on omega 1. It depends on the phase. So because of this, you see that I control the qubit rotation by generating an appropriate pulse with the right phase, right frequency, and also right shape at the right time for the right duration. And that is what I said earlier here to do the 1 qubit. Okay? So with this, you trust me? All I need to do is just change the shape of the pulse, the frequency and phase. I will be able to rotate it from any point on the broad sphere to another point on the broad sphere. And that is the meaning of 1 qubit gate already. If I can rotate, if I can do what I just said. So that is 1 qubit gate. So good, you know how to implement it. You need to draw the right circuit. You need to give the right pulse. How about 2 qubit gate? Now here I just want to first emphasize one thing. I-swap gate is a special gate, but it is also an entanglement gate. Now you may say, isn't that is CNOT? CNOT is just one of the entanglement gates. And I can use it to build CNOT. Okay? So in different quantum computing architecture, due to their physics, they are different. So they have different native entanglement gates. So for superconducting qubit, one of the native gate is I-swap gate. So how does it work? This is a very simple example. I have 2 qubits, but more importantly, they are flux tunable qubit. Okay? Although I did not draw 2 Josephson junction, but here we assume it is flux tunable. So it means I have 2 Josephson junction. So they have different frequency. One may be omega 0.1, one is omega 0.2. So when they don't interact, they don't talk to each other, just like the radio, right? You have different frequency. They don't interact with each other. But they are coupled through a capacitor. When we want to have the 2 qubit gate, we will tune the second qubit by applying a flux, which I mentioned earlier, so that omega 02 equal to omega 01. Okay? And then with that, then they will talk to each other and interact with each other. And this is the Hamiltonian. Okay? Oh no, this is the gate, but this is the Hamiltonian. It's equivalent to this gate, right? Because the gate is the exponential of Hamiltonian. You turn it on the right time. The time is 2 pi h bar divided by 2g. G is the coupling factor, how strong they are coupled. And then you get this gate, and this is the so-called I-swap gate. With I-swap gate and some 1-qubit gates, you will be able to build the CNOT gate. So here I show you how we build the 2-qubit gate in a superconducting qubit. Basically, you need to have a coupler, and also you need to have a mean to let them talk to each other. In this case, we tune the flux by tuning the bias current so they have the same frequency. So now we can implement any 1-qubit gate, also an entanglement gate. Then we can use it to build any quantum circuit. So it can implement a set of universal gates. Okay, so we have two-level system. We know its decoherence time is reasonable. We know that how to do 1-qubit gate and 2-qubit gate. Initialization, we don't mention, we know it works. How do we read out the information in a superconducting qubit? What we do is to do something called dispersive readout. So let's understand how it works. First of all, here is a transmission line. Now this one requires you to have some knowledge in microwave engineering. This transmission line means that I apply a pulse on the left. It's not necessarily everywhere it will come out from the right. V out divided by V in, where I put S is the frequency domain. If you don't know, just treat it as V out divided by V in. It's what we call S21. It's a S matrix, scattering matrix. If you have a lot of signal coming out, then this is 1. When you don't have signal coming out, this is 0. If it's a regular, well-defined transmission line, then it will always have large S21 for any frequency. But if we interrupt it with a resonator, we talked about resonator earlier, it has a resonant frequency, right? Omega R equal to 1 over square root CR LR. If you don't know about that, fine. You just trust me. It has a resonant frequency, just like a bridge. You stand on for every bridge, it has a resonant frequency. Okay. Now, because of this, only when the frequency is at the resonant frequency of the resonator will go through. So basically, if you try to plot the S21 as a function of frequency, you will see something like this. I plot the magnitude. And it will go through when this is equal to omega R. When you are at resonant frequency, it will go through. For other frequency, you cannot go through. Okay? So nothing special at this moment. But we couple the resonator to the qubit. Again, this is a Josephson junction. Why we need that? Because we use it to serve a non-linear inductor. In parallel with a capacitor, this is the so-called transmon qubit, which I did not discuss this time. But basically, it's just a superconducting qubit. It's coupled to the resonator. So it turned out that if the qubit is at state 0, it will change the resonant frequency of the resonator. So you might see something like this. If the qubit is at state 0, But if the qubit is at state 1, the resonator will change to a lower value. And this effect is called the cross curve. Okay? It's not difficult to understand physically because think about that. If this is the bridge, it has a resonant frequency. Whether there is an extra person standing on the bridge, it's going to change the resonant frequency of the bridge, right? So if I want to know if there's someone standing on the bridge, I actually don't need to look at the bridge to count the people. I just need to measure the resonance frequency. This is something similar, although not a very perfect analogy. Okay, so that is how we understand how we measure the state of the qubit. So I already mentioned this, and the change of the frequency is cross curve, and this is something we call the dispersive shift of the resonator frequency. So what we will do is shoot a microwave pulse at the original resonant frequency, but we don't look at the magnitude because the magnitude is the same, whether it's excited state, E means excited state, or ground state. We look at the real and imaginary part of the signal, and you find that when it is at ground state, this is positive. When it is at the excited state, this is negative. So basically, we're trying to find the phase of the signal, how the signal got changed, how the phase of the signal got changed when at different state, right? So we will say when it is positive, then we know it is ground state. When it's negative, then it's excited state. We can do a transformation, just rotate it, then we can become something Qi broad. Now you see that this is larger because now I include noise to it. If there were no noise, it would just have one point. Then as long as it is on the upper plane, I know it is 1. When it is at the lower plane, I know it is 0, right? But because of noise, you need to be very careful. If the shift is not enough, you will get error. For example, let's say it's at ground state, you can also reside on the upper plane. And then when you read it, you find it's positive, then you thought that it is actually 1. Then this becomes a readout error. So let me go for, so we already talked about all the important criteria that allow the superconducting qubit to work as a quantum computer. But is it possible to make it larger? Because now you see that, for example, they have a large size, and how do you incorporate many qubits on the chip? So there are many possible ways. One is that you can have flip chip. You try to bring 2 chips together to increase the density. You can also have 2 chips. This is 1 chip. This is another chip. And then you have a common substrate. You just bond the chip to this substrate. And then you can add this metal, superconducting metal wire. Then remember how we do a 2-qubit gate? Basically, this is a 1 qubit flux tunable, another qubit flux tunable, right? You see this loop? You just connect this wire, and then you have capacitor, right? But this is more special. This is a tunable coupler we did not discuss before, but it is just another type of coupler. But anyway, you see that you can just connect them together, and this is quantum because they're in superconducting state, and then this part only serves as a transmission line, so the whole system is still communicated in full quantum way, not through a classical way, right? So then you can have put many chips together on a bigger substrate. For example, Rigetti, right? They already done putting 4 9-qubit chiplet on top of this, right? So 36 qubit. By the end of this year, they plan to have 100 plus qubit, right? IBM, by 2028, they plan to have 120 qubit chip, but put 9 of them together, then you have 1000 qubit, right? And eventually, 5 years further, they hope to have 2,000 logical qubit. Logical qubit means that you have many physical qubit. We did not discuss this, but as we said, because of the error and also the short decoherence time, you need quantum error correction. You may need about 100 to 1,000 or even more physical qubit to have one logical qubit. Okay? And you may also need quantum transduction to enable fridge-to-fridge communication, etc. Okay? So here I can move forward to spin qubit. So again, what we want to know is how we encode the qubit, right? So first of all, we need carrier. We use electron or a hole, right? If you have learned semiconductor, you know there are electron and hole in the system. If you have not learned semiconductor, you just accept it, maybe electron and then hole. Now, the main point of electron is that it has something called spin. Spin is a characteristic of elementary particle. It's just like the charge. We can think it as a charge rotating, which is wrong because electron is a point charge, so it cannot be rotating. However, if you want to think in this way, usually it works. But anyway, you just accept it, electron has spin. Just like electron has negative charge. Okay? Right? We always accept electron has negative charge, right? Since we are in primary school or elementary school. Right? It's the same as spin. Right? If your teacher taught you at that time electron has spin, maybe you will just accept it. So because it has spin and it's a charged particle, it has something called magnetic moment. And if you have learned magnetism before, you know that magnetic moment under an external magnetic field will have energy, right? Which is called Zeeman splitting. So if you are spin up, and what is the meaning of spin up? Is related to the direction of the external magnetic field. When there is no magnetic field, spin up and spin down has the same energy. You cannot distinguish them, right? Because there's no interaction energy. Spin by itself has no energy. So spin up and spin down has the same energy, right? You just think about, let's say, a good student. One student study very well, one student never study. If there's no exam, you cannot distinguish them. And if you have exam, you can distinguish, okay, this one has higher GPA, this one has a lower GPA. It's just like that, right? So that form a two-level system. It is very simple. Naturally, we have a two-level system due to this so-called Zeeman splitting. Okay, but because of this, you find that its energy depends on magnetic field. So if there's any magnetic field around it, you have a lot of noise, right? Any magnetic field that you don't want. For example, in silicon, you have different isotopes. You have silicon 28, silicon 29, and silicon 30, I think. And there are lots of silicon 29. Silicon 29 has nuclear spin because it has odd number of neutrons. So if you try to build a quantum computer using a regular silicon wafer, you will have a very bad spin qubit because the silicon nuclear spin will create magnetic fields and then you mess up your system. So you usually need something called purified silicon, in which you will have most of them are silicon 28. Okay? So that is one of the important things. Once you have a purified silicon, then you have a very good qubit. So that is the encoding of a silicon spin qubit. Now on the right you see, if you have heard about that, this is something called FinFET, three-dimensional transistor. But anyway, it can also be implemented on silicon on insulator or planar transistor. The goal is to create a quantum dot, a potential well, so you can capture one electron. Okay? So basically you create a apply the appropriate gate bias so that you only trap one electron in a space. And then you apply an external magnetic field. Then you have a silicon spin qubit. Now there are other spin qubit, for example, hole. The good thing about hole is that it have a very strong spin-orbit coupling, which probably most of us don't understand, because if you have not studied semiconductor physics or solid state physics. But basically this just trying to say that they can be controlled by electrical pulse, which is good. I forgot to say, for spin qubit, if you want to operate, you need to apply a magnetic pulse instead of electrical pulse. Remember, for superconducting qubit, I apply an electrical pulse. Here I need to apply a magnetic pulse, which I will show you later, right? Which is not convenient, because you know that generating and controlling magnetic field is not easy. It's much more difficult than generating and controlling electrical pulse or electric field, right? But if you have whole qubit, it's possible to control it through electrical mean. However, that also means that it will be susceptible to electrical noise. And on silicon, you should know that we have a lot of defects at the oxide or some charge, acceptor and donor, a lot of charge that can hurt the decoherence time. Okay, so this just, you know that you have something like that. Here we only consider electron spin qubit, which has two levels because of a constant magnetic field, and we are going to control it use variable magnetic field. So I show the decoherence time first. This is the T1 time we discussed earlier. It has some special measurement, but the effective T1 time is very long, 2.8 seconds. Remember, the superconducting one was about 200 microseconds. So that is like about what? 10,000 times longer. Okay? Now, and also it is at 1.5 Kelvin. And its T2 time is also very long, 0.12 microsecond. The one I show you was only about 50 microsecond, right? This is 0.12 millisecond. I say it wrong, millisecond, right? So it's again pretty long. So looks good, right? But however, the problem is that it's difficult to have a good 2-qubit gate that we will show you later. So how do we implement a 1-qubit gate? So here you need to trust me again. The way we do the 1-qubit gate is that we have this external magnetic field. This is the Zeeman splitting. So spin up and spin down has different energy. If I want to do 1-qubit gate, what we want to do is to let it rotate and eventually go to here through something called rapid oscillation. And how do we do it? Is by applying a small external AC magnetic field. You see, this is cosine omega L. And you can apply at different direction, or you try to manipulate it. But anyway, this is the simplest case, right? If we do it right, you can let it rotate about any axis, which I mentioned in my book also. But it just give you an idea. But what does it mean? How do we implement? So on the right is a top view of a chip. This is just a regular silicon chip, just like the chip in your computer, except that they do some special layout. For example, it has different metal layer, right? You see this metal layer? You call it reservoir, quantum dot, and then it has some single electron transistor. It doesn't matter. All this trying to do is to create a quantum well to confine one electron here. And some of them are used to let it talk to another qubit by changing the barrier. Some of them are for readout, which we have not discussed yet. So now you just agree that it uses many gates to create a quantum well to confine the electron. Okay? And we apply an external magnetic field, B0. So with this one, it means if you're going to the right, this is spin up. If you spin to the left, this is spin down, because up or down depends on the magnetic field direction. Okay, now how do we create this AC field? Just like how we did the first qubit, right? We have a metal wire. We pass through a current. Here we call it IESR, which is electron spin resonance. We pass through a current, but this is not a DC current. It is an AC, right? So you go back and forth, go back and forth. And because of that, then you have this magnetic field going clockwise, anti-clockwise, clockwise, anti-clockwise. The qubit here then will feel a magnetic field perpendicular to the screen, just like this, oscillating up and down, from pointing up to 0, pointing down to 0, pointing up, and then you create a 1 qubit gate. And that is the implementation. So again, you see everything is classical, right? Except that we need to create a magnetic field. How do we connect this? Still, these are controlled by the room temperature electronics, although we try to bring it to lower temperature, which I will show you later. So this is 1 qubit gate. How do you do 2 qubit gate? Now here I have a cartoon, draw the cross section. Again, we have the gates to control a quantum dot. So this is a very simplified picture. You need different gates. Like here, you have 4 gates, right, to form the dot. And then the bottom, you also need to confine it through maybe heterostructure. But just agree that we do have a 2 electron here. And then you have external magnetic field, so that you have 2 levels. So this is a 1 qubit, this is another qubit. And of course, you can apply magnetic field to do 1 qubit gate when you want. But when I want to have a 2 qubit gate, what we do? We actually will lower the barrier. Here shows the energy under it. So here I actually should have done a better job. This actually have another gate, which is called the barrier gate. These gates will control the potential between these 2 quantum dots. What we need to do is just lower the potential so they will interact. The electron will see each other. And then after a certain time, they will have, this is just an example, because for example, this is a control phase shift gate. Remember I told you that different architecture has different native entanglement gates. For silicon, I-swap gate is not that good, right? CNOT gate is not that good, but control phase shift gate might be better. There are other type also, but here show the control phase shift gate. Now you see in this process, we don't have any magnetic field. We do have this constant magnetic field to make it into qubit, right? Because I need 2 levels. But the interference is completely electrostatics. And that's why it is very sensitive to the charge nearby. And as a result, the 2 qubit gate has relatively low fidelity. But anyway, that is how we form the entanglement gate. What we do is just to bring them together, let them interact. How do we read out the state of the qubit? We can have something like the superconducting qubit, something we call reflectometry. Here we show another not so good way, but it's pretty common, is so-called spin to charge conversion. To read out the qubit, what we are trying to do is to know whether it's spin up or spin down, right? Whether it's 0 or 1. We cannot read it out easily, right? Because to read the spin of an electron is really not easy. We might need to have a photon and see the energy change, etc. So what we do is to convert the signal to charge signal. So here show a qubit in a quantum dot, and next to it has a reservoir. The reservoir is just a metal wire. You have a lot of electron. And next to it have another transistor called quantum point contact transistor. This transistor has current which is very sensitive to the charge next to it. So they are separated but it is sensitive to it. When there's no charge, it has a large current. When there is a charge, it has a small current. So that's how it works. When I want to read out, I will lower the potential so that the qubit and the reservoir are close to each other in terms of energy barrier. Now, if it is spin down, which has a higher energy level, it will tunnel, the electron will tunnel into the reservoir. Very easy to understand, just like a reservoir, water reservoir. If your water higher energy than the surface of the water, it will go in, right? And later, one of the water molecule may come back, right? It's just the electron can tunnel to the lower energy level. Now, when this one go from here to here, then it means the quantum dot has one less electron. So the current of this point contact transistor will just jump up. But then later, when another electron tunnel back, then I have electron here. So the current here will go down because it's very sensitive to the charge. On the other hand, if the state is spin up, which has a lower level, it is below the surface of the electron reservoir, just like water. It is full already. You cannot go into it. So the current will never change. It's just low. And the way we read out the qubit is that we just try to start the reading, bring it close, and then if we see the current has a bump, then we say this is spin down. If we don't see anything, we say this is spin up, right? There are many other methods, but I just want to show this method, which is pretty interesting, spin to charge conversion. So we have two levels. We know the decoherence time is pretty good. We have 2 qubit gates and 1 qubit gates, everything goes well. Although the 2 qubit gates has low fidelity, and we know how to read out. And so silicon qubit can be used as a quantum computer. But in the future, as we just discussed, we need to integrate lots of qubit onto it. Well, this is good because we have a silicon fabrication, right? Like in Taiwan, TSMC, UMC, you have all the technology to build billions of transistors together. So no problem. You see, we can make very tiny gates or whatever, right? We also can have hetero integration with 2 layers. On the top, this is just like a memory decoder. At the bottom, it will be the qubit. And then you use the top to control the bottom. And then if you do it right, you will have some layout that is very suitable for error correction. And this is nothing new. We have done this in GPU, high bandwidth memory to GPU, right? This technology is very mature. Of course, the problem again is how can you maintain a high fidelity for the qubit? One another large-scale integration possibility is that now we still have most of the electronics. Let me remind you, you have this layout, reservoir, everything. All this, every qubit need to have one control line going to the electronics, right? To determine when you are going to turn on the 1 qubit gate, when are you going to turn on the 2 qubit gates for how long, right? How are you going to do the readout? All these are controlled by classical electronics at room temperature. So this is not good. But because silicon qubit might be able to work at a higher temperature, as I showed you earlier here, even for this 1.5 Kelvin, sorry, I say it wrong again, it's 1.5 Tesla. This is the magnetic field, but at 143 millikelvin. But there are some silicon qubit work pretty well at 1 Kelvin, right? So we may be try to bring this closer to room temperature, 0.1 to 4 Kelvin. And we also can have the cryogenic interface, CMOS, put at 4 Kelvin, right? They have a larger cooling power. Look at this, at 4 Kelvin, I can have 1.5 volt of cooling power. But at 20 millikelvin here, I can only have 20 microwatt. So by bringing this closer, you might be able to have a better large-scale integration for using silicon qubit. Okay, I do have more time, but this is for silicon qubit. Maybe we can spend. Yeah, so these are the reference. So now I want to talk about the photonic qubit. So this one, maybe it would be good to cover everything, so I'll be faster now because this is kind of extra. Photonic qubit and trapped ion qubit. So again, how do we encode the qubit for photons? Now, photons cannot be stationary because they are light. So how do we encode it? We have two paths. These are the waveguide. Photon is moving, right? If photon is on the top, we say this is state 0. If photon is at the bottom, we say this is state 1. So this is something called dual rail encoding. You have two rail, right? So it can be have a superposition. Photon can be on top or at the bottom. So it is alpha top plus beta bottom. That is quantum mechanics, right? An electron can be in the cup or outside of the cup, right? So that is how you do it. Now, for photon, something very important is to generate the photon, right? For other qubits, superconducting qubit, you make it, fabricate it, I have a superconducting qubit. Spin qubit, just grab an electron, I have an electron spin qubit. But for photon, I need to generate a photon. Now, this is not trivial because photon is moving, and generating photon is a stochastic process. It is not always there. So what people use is something called spontaneous four-wave mixing. Again, this is physics, pretty deep. We don't need to understand well. But the point is that you pump it with two photons. So you have a laser pump into the generator, and then you will come up with two different photons. But they are related to each other, entangled, right? One is the so-called idler, or we call it herald photon. It's the herald. So basically, how do you know that we have generated photon we want? We will have a photon detector. When we find that a herald photon is generated, then we know that another photon has been successfully generated. This one, we don't want it because once we measure it, it is useless. But then this photon, then we know a photon has been generated, then we will process on this photon. Okay? Here just to show that they use a ring oscillator, resonator to generate the photon. And you can see that by adding different amount of power, the generating hertz rate will increase. But still is talking about generating 20 millions of photons per second, which is not a lot. And some of them can get lost. So this is a very important procedure in photonic quantum computing. So once we generated the photon, then depends whether it's on upper or lower path, we encoded 0 and 1. How do we detect the photon? This is relatively easy. Probably you know, just like a camera, right? If you take a picture, you see the light, then you know there's a photon. But of course, we need to detect single photon. So what we do is using a superconducting nanowire single photon detector. So for a superconductor like this, if you don't know, a superconductor will not be a superconductor if the current is too large. So when the current exceeds a certain level, which we call it the critical current, even you are at low temperature, you will lose the superconducting state. Okay? So we will have a superconductor bias at where just below the critical current. So it is still a superconductor. Now when there's a photon hitting it, it will generate electron pairs, no longer Cooper pairs, which we call it quasi-particle. But doesn't matter, you just trust me, when you generate here, you will create a resistive spot. So all the current will go to the side. But then they are just below critical current. Then here the density will increase. As a result, they will go back to the normal state. And then this will be no longer superconducting, and then you can measure the voltage drop, because a superconductor does not have voltage drop because it doesn't have resistance. After absorbing a photon, you have resistance, then you will see the voltage drop. And that is a very efficient photon detector. Now, I need to emphasize one thing. If you forget everything, you need to remember, photon can operate at room temperature very well, our optical fibers or etc. So basically, a photonic quantum computer can operate at room temperature. Maybe you want to operate a little bit more if that will help a little bit, but it works well at room temperature. However, the photon detector need to go to 4.2 Kelvin, but still very high compared to superconducting qubit and silicon qubit, right? Superconducting qubit need to go to 20 millikelvin, right? And silicon qubit at most maybe 1 Kelvin or lower. Okay, so that is the good thing about photonic quantum computer. So we know how to encode it, how to read out. How do we do the 1 qubit gate? So this becomes a little bit complicated now, actually. For me, when I learn photonic quantum computing, I have more difficulties. Now, first we can use the classical photonic circuits, silicon photonics. For example, the photon can get an extra phase if we add a delay on the optical path. Remember, we say the photon is traveling here. We just hit it up, and then the refractive index will change, the light velocity will change, and then you will get an extra phase. You can also use spin splitter or direct coupler to form different type of 1 qubit gate. Particularly this one is pretty instructive. It's like a regular mass center interferometer. If you have not learned this before, that's fine. But basically, you see that I have two paths. It will have an interaction, so you have some probability of going up and down. At the bottom, we may heat it up, so it has different temperature. Then you have different delay. As a result, you can create a quantum gate like this. You can also have 2 qubit gate using an architecture like this. And here you see that we're using CNOT gate. This is the control gate. If you remember from last talk, you have a target gate. When the control gate is 0, don't do anything. When the target gate, control gate is 1, apply NOT to the target gate. And this is dual rail encoding, right? So if it's on the top, it is 0. Photon at the bottom, it is 1, 0, 1. You just go through the math, you find that this can implement a CNOT gate. However, not always successful, because you need to do measurement at the end. And then only 1/9 of the rate will be successful. But if it fails, you just do it again. Okay? So there are lots of stochastic things, issue in photonic quantum computing, including the photon generation. But nowadays, there is a more useful or more promising architecture for photonic quantum computing. Instead of using all these gates, what they do is to do something fusion-based quantum computing. Now, it's difficult to explain here. It's pretty profound. But basically, what it means is that you generate some qubits and make them entangle first. And to make them entangle, you can also use something called Bell fusion. So this is an entangle system. This is another entangle system. I try to do a Bell basis measurement on this two. This will be gone once I do the measurement. But then these two will get entangled, and that form the cluster. Now, and then how do you do computing? To do the computing is you do some special measurement on some of the gates using some special method, like or measure some particular qubit on a particular basis. By doing different measurement, eventually is equivalent to quantum computing. Okay, you first entangle everything, and then you do some appropriate measurement. That is equivalent to quantum computing. So that is called measurement-based quantum computing. Now this one has one advantage because it's already enables some topological error correction in this process. So that is what psi quantum, right, is doing nowadays. Okay, so that is photonic quantum computing, right? I will skip the uniformity thing, right? So let me just complete the lecture with the trapped ion so you have some idea what it is. So now we go to trapped ion. We need to know how you form the qubit. But first of all, what is the carrier? Silicon qubit is an electron spin, right? But here, for example, we use ytterbium ion. So you confine them in the air. Use electric field, DC electric field and AC electric field. So you have a string of ion, like a crystal lattice, floating in the air. So this need to be in vacuum. It's very important to put it in vacuum. And each ion, they have something called hyperfine structure. I won't explain that. But basically, this is the interaction between the nuclear spin and the electron generated magnetic field. Electron is rotating in this ion, right? So it generates magnetic field. And your nucleus has spin, right? Proton and photon. And that nuclear spin and that magnetic field will create 0 and 1 state. And this is the qubit state. Now, how do you read out the qubit state? Now, if it's at 1 state, what you do is to shoot a laser pulse of certain energy. It will be excited to another level. These are not the qubit level. But in an atom, you have many levels in an ion, right? So this is one of the level exists there. You will excite it to this level. And after that, it will decay. Then what happens? It will emit a photon, right? And then you will just absorb and emit. So imagine you're shooting a laser to an ion, right? This is the ion, and you're shooting the laser. Your laser keeps shooting. So you will absorb, emit. But when you emit to different direction so that you can see it. So by counting the number of photon emitter, you know that it is at 1 state. If it's a ground state, this energy is not enough. So you suppose will not get any photon. But there are sometimes some error. We don't go into details. But the point is, low photon is 0. When there's photon, it is 1. Okay, so that is how you do the qubit readout. Shoot a laser into one of these ion floating in the space and see if there's light coming out. If there is, then you know it is at state 1. For 1 qubit gate, I will go also very fast because this involves a lot of physics. What we do is something called stimulated Raman transition. But doesn't matter. Basically, you just shoot in 2 laser pulse, again laser pulse, with some difference in energy. Then it will go to a virtual state coupled with virtual states, and in this process it will also emit 2 photons, but this is not important to us. The most important thing is if you go to the physics, this is equivalent to a gate operation. It will perform rapid oscillation, right? So here we don't go to the physics, we just tell you that shooting 2 laser pulse with 2 different frequency, the difference equal to the qubit frequency, then you will be able to do a 1 qubit gate, which is great. How about 2 qubit gates? A lot of things, so I won't go into details. I just want to point out something very important. What we do is we shoot a laser. For example, I want to do an entanglement gate between this one and this one. What do? I will shoot a laser pulse to this one, and then shoot another laser pulse to this one, and then shoot another laser pulse to this one. Then I successfully form a control C gate. Oh, that's interesting. Why? Why there's entanglement? I shoot laser pulse to here and here. They are not talking to each other, right? Isn't that? And that is because this is an ion train. So they are just like a wave, a lattice is vibrating. It has some mode. And because they are in the train, actually in this process, we are going to borrow the energy of the train and thus cause some entanglement between them. Okay, as a result, we have this control phase shift gate. But because of time, I don't go into detail. Okay, integration is also important, but let me just also skip here. Okay, So, and these are the reference that I have for trap ion and photonic qubit. Okay, so I will stop here. Basically, I have covered most of the thing. And let me know if you have any questions.